I bought a calculator from there
Oh, yeah.
for $75, and that's basically
Oh, basically,
MSRP
when
per
the
unit.
semester's done, that's where.
All right,
Can we get me
it's rolling.
You're going to find that as we're going through this course, there's certain topics that I can do cold and certain topics where I have to keep referring to my notes. Obviously, I'm still in the referring notes section. I am going to sort of list out some differences between pressure and stress. They have the same units, but there are some fundamental differences between them. And so pressure comes from an external source, where officially stress is internal. Even though we talked about, I'm applying a force to stretch it out, but the material is trying to pull itself back together again. Trying to return to equilibrium. This is compressive. Always compressive. And this can be from compression, shear, which we'll talk about in a moment, or tensile.
So if it was compressive, it would be, if you had like a piece of metal that you're pushing in on it,
Yeah, that would.
and it's trying to push back against you.
Right, so officially you're applying pressure to it and it's experiencing stress.
Okay.
Same thing apply like air moving through a pipe. Like, is that compressive or?
If this one, which aspect, I was picturing the air pushing against the pipe.
Oh, okay. I was saying where the pressure is moving particles through a pipe. That's sort of what my section of the field does. We do dust collection systems.
Yeah, all right, so part of my hesitation is at what point do you stop talking about force and start talking about pressure?
Yeah.
So there would have to be a pressure differential to get air moving through the pipe. Because there are forces acting potentially on both ends unless you've got a pure vacuum on the one end, in which case, market that thing. So you've got some pressure differential, pressure pushing on both ends, so you have this, in essence, a net force acting on the particles with a net direct, so net force would be in one particular direction. So it is pushing, so in that case, yeah, compressive is you're pushing on things.
Okay.
Is that, did I get you?
Yeah, I think that's,
Okay.
that sounds right.
What is shear stress? Is that like cutting?
That's like,
The other reason I brought this link in,
Oh,
shear.
oh, it's sliding against each other.
Yeah.
Like what Alex was saying.
And then tensile tension pulling. The pressure is, the force is perpendicular to the surface. And this can be any angle. And then mathematically, pressure is a scalar. Where stress is not actually a scalar, even though we treated it as such. If you really get into the hardcore aspect of it, it's a second order tensor.
What's a tensor?
A tensor is, a vector is to a scalar as a second order tensor is to a vector. It's basically, you're adding an extra dimension to the vector, properly to,
what
it's
is,
being recorded right now. Pardon?
what is the dimension that you're adding?
I can express a vector by a specific direction, whereas if I properly express a tensor, I need to express it in multiple dimensions simultaneously. It's not like there's a net, it's not like I add them all up and it's in a particular direction. There are, my memory has been a while since I officially dealt with tensors. I think for a second order tensor, there's 3 dimensions probably have to be expressed independently of each other. I don't know if I quite captured it. As you can tell, when I had to deal with tensor calculus, I had not taken a math class. It was that physics attitude of, you don't need to take the math class, we'll teach you all the math you need to know. If a physicist ever tells you that, don't buy it.
Oh, well, yeah, I kinda learned that firsthand.
Yeah. I'd also dealt with tensor calculus while I was taking a general relativity class. My goal in the first test for general relativity was to understand the question. I did not succeed. That, of course, kicked my butt. And I blame Bill Baird, who's now a professor somewhere in Georgia. He really wanted to take it, so he convinced a number of us to take it. At least I knew what I was not going to pursue with my life. This is measured directly.
How are you?
And this is measured indirectly. The times that I've seen stress being measured, basically it measured force and you knew the area and you calculated it.
It's like, our department, maybe the strain gauges, where like they measure the length using bridges and stuff. That's what, like, the posters are in the hallway. In Hoosier, they have like all those posters on the wall.
Sure.
They built strain gauges.
They built them.
Yes. Whatever, never
I
mind.
feel like you two were not part of the same conversation. Or is it? Years ago when I was working in Columbia, South Carolina, I was teaching in high school and there's this, I have to take the Beltway in order to get to school. And there were a couple of places where the cops generally were hiding for the speed trap. And I had a student who was talking about it. He said, you know where the cops usually are? It's after that second bridge. And I'm staring at him blankly, thinking, I've driven that path 500 times at least, and I could not picture at that moment the second bridge. I don't know why. And as I was driving back, I thought, how could I not picture this? I've done this so many times. I don't know if you were,
Yeah,
if I channeled that to you.
I'm sure if I go to Hauser, I'll know what he's talking about.
I will not be there.
Yeah, it's just something I imagined for the last few years.
All right, so let's talk a little bit about shear. So again, you're pushing on it, causing deformation, sort of against the grain, causing it to tilt. It's not stretching out, it's not compressing, it's deforming at an angle. So I have some box right here. This side is fixed, and I apply a force up here. You're going to get some deformation, and we'll go for that typical stunning visual effect with a different color. So there's this angle here, phi. And this has been stretched, and I'm going to keep the same letters as I'm using here. Just like this down. And as I step back and look at it, I just want to point out that's supposed to be a rectangle, not the trapezoid that I think I drew.
Parallelogram?
Well,
That do. Yeah, they're both parallelograms, just one happens to have right angles. So, when you want to look at stress and strain, it's a little bit different here because the deformation is not something so easily measured. And so, try to do it in the right spot. So we look at the shear modules, which again is stress over strain. Shear modulus. The symbol that your textbook uses is S, but you will also sometimes see as a G and sometimes see as an eta. but that's what your textbook uses. And so force over area, that area is the cross-sectional area right here. So it's the area of the face on which the force is being applied, divided by the strain, which is the tangent of phi. And I changed notation in here, so. So this distance here is also d. So now we use some right triangle trig here. That's that triangle right here with phi. This length here is d, and this is L. So what trig function involves the opposite side and the adjacent side? Tangent phi is d over L. And so you could see this as f over a over d over L, or FL over dA. But then we could have also employed the small angle approximation. Have you dealt with the small angle approximation before?
That sounds new to me.
Okay. All of you have calculators, or most of you?
Yeah, let me pull mine.
So let's let phi be 0.01. What is the sign of 0.01? Now notice, when I wrote 0.01 here, I did not write any units. If I do not write units, what is understood to be the unit for an angle?
Radians.
So this is radians, sine of 0.01 radians, and also do the tangent of 0.01 radians.
The sine is 0.00991, or no, it's 9 repeating.
Probably not on forever, but. Okay.
And then tangent is 0.010000.
All right.
Notice they're practically the same. How many degrees is 0.01?
Radians?
0.01 radians is how many degrees?
5. Well, 1 radian is like 53.
Something like that. So it'd be about 0.5
Yeah.
degrees. Let's make it bigger then. Let's go 0.1. So phi is equal to 0.1, the sine of 0.1 radians, and the tangent of 0.1 radians.
Uh,
0.998 and then 0.100.
1 point.
No, 0.100.
Oh, no, thank you. Notice we're still roughly about the same. So the small angle approximation recognizes this. And so if the angle is much less than 1, when you see the double less than symbol, that means much less than, then phi is approximately equal to the tangent of the angle, which is approximately equal to the sine of the angle. As long as we're dealing in radians. And so this can also, if the angle is small, so obviously not in the case when I dealt with the slinky, but if the angle is small, you can also write f over a over just phi, because tan phi and phi are roughly the same. Just F over phi tan. So that in essence is the shear modulus.
What is that?
Somebody's- I think they're watching a movie over there.
I assumed it was the student and teacher just so happy they need to sing.
Yeah. They're watching something.
Yeah, it sounds like one of those stereotypical UFO tractor beams.
I'm pretty sure it was somebody's thinking.
Yeah, I like an opera scene.
Yeah.
Small angle approximation we will deal with again. As a recollection or a, nudging in the direction, remember that physics was developed pre-computers, so they came up with all of the tips and tricks that they could.
So that's basically just, if it's much less than 1, it's close enough that you can,
Yeah, just drop the tan or sign.
yeah, that you can kind of just use it as that number.
Yes.
Rather than finding the tangent, or the arc tangent of it.
Yeah. And typically when you see much less than, there's the 10% rule. Physicists, if phi is 0.1 or less, then they would typically use it. Even though I think if you're off by 5% when you get to 30 degrees, and I think you're off by 10% somewhere around 45 degrees. And so you've got a little bit of leeway there, but you start sacrificing at some point. And there's a lab that, I guess 2 years ago, I did with a group, 133, where I went ahead and assumed small angle approximation, and we just started we were getting much further off than I was expecting. And then we did not use the small angle approximation, and we were like 1% off. All right. And then the last one from this chapter in terms of moduli is the bulk modulus. Which is volume stress over volume strain. And it looks a whole lot like the one-dimensional when we were dealing with Young's modulus. This is still force over area. The strain, instead of being the change in length over length, it's the change in volume over volume. So as I push on this desk, the volume is going to change slightly. So we do force divided by the area, and then however much the volume changed. But this is basically the three-dimensional version of it. And then the textbook talks about compressibility. It's just the reciprocal of modulus. Now, there are some additional things where they just mentioned in the last section of that particular chapter. I think you can just as easily read that on your own. Let's talk about this for the most part is chapter 13. So let's talk about the quiz. At the end of the chapter, typically what happens at the end of the chapter when I say I'm done, other than I'm done, I'm assuming that as you work through problems, you'll have questions. And so it'll cover things that I forgot to mention in class or things that you just didn't quite catch completely. If you go to the Blackboard site, under coursework, chapter 13, you should see assignments. These are textbook assignments with a cut and paste of the solutions that come from the publisher. Occasionally, there'll be an additional comment from me if there's what I feel is need for clarification, or if there's a mistake in what the publisher has, and it's been brought to my attention. So, if you go under assignments, you pull up the document, you're gonna see a set of problems coming from chapter 13. You are not handing that in to me because I gave you the solutions. I would assume everyone would get 100% on it. What I'm gonna do instead is, a week from today, I generally like to have one class in between. I'll start off the class with any questions from chapter 13. I should start out Wednesday also doing the same thing. And then you'll ask questions or not, and then we'll do a quiz. The quiz, I'm going to take 2 of the questions that are assigned, I'm changing numbers, that's going to be the quiz. So, if you like surprises, you don't need to look at the problems. Not my recommendation, I had only one student I think really pulled that one off, but he was taking that class for the second time. But you should know how to solve all the problems. At least you've seen a problem like what you're going to get on the quiz. This is partly the regurgitation point of the course of, hey, I worked through that problem. Oh, the numbers are changed. Let me do the exact same thing except put in these new numbers. I did have a student once who memorized as much as possible. She answered the question using the original numbers from the problem. Yeah. It's that debate of, she did all the steps except used all the wrong numbers. What do I give credit? How much credit do I give for that? Anyway. Other memories just got dredged up then. And I'm just getting mad. So, instead of taking it out on you, I will not obsess over that much right now. So, any questions about the quiz that you will have next Monday?
Not yet.
Yeah, I can't think of anything.
Okay,
Are you gonna do the post-physics re-lecture that we were doing in Kelly Sass's class?
Sure.
Done that soon. Right. Any questions? All right. We have 5 minutes.
You want this plastic back?
Yeah, I'll take the plastic back.
Yeah, I gave you mine back
I'm
after
assuming-
a strip. I think that's, or probably not. You'll notice mine.
No. Yeah,
Yeah, this
as
is
long as
the-
there's something that I can, yeah, there we go.
Yeah, this is the one
Okay, that works.
That's one plastic deformation.
We're not necessarily gonna do this every time, but I'm gonna go ahead and say it does not seem worth starting the next chapter at this point. We'll start it on Wednesday. You do have the lab on Wednesday also. The lab's not gonna take the entire 2.5 hours. So we'll do the first part of Wednesday. We will be in the other room, the room that we're supposed to be signed up for this one. So we'll be in the other room. We'll start out doing class. At some point, one of you is gonna say, weren't we supposed to do a lab today? And then I'm gonna go, oh yeah, that's right. And then we'll do the lab. As always, celebrate the fact that you're taking physics. It is the best subject.
It is interesting.
It can be, but I can make it as dull as possible if I need to.
Oh boy.
Don't tempt me.
I am curious what kind of experiments we would be doing with light and sound.
absolutely magnificent ones. And some of them even get good results. True story.
I'm excited.
I mean, they're just some classic labs that we'll be doing. Eventually finding speed of sound, we'll get speed of sound on a string. I'm not quite sure. Oh, I guess, I was about to say, look on Blackboard, but I'm only showing one at a time. Or I showed one as we go. So,
Still there.
The table is still there.
if you email me, I can send you a list of them if it's.
It's a little-
Would you like me to stop the?
I,
Oh, yeah,
I'm
that's what we
I'm
did.
saying,